So, what's the smartest move you can make when you know absolutely nothing about your opponent? Today, we are diving into a really powerful and kind of counterintuitive strategy for winning with nothing but pure logic, even when you're facing total uncertainty.
All right, imagine this. You're sitting down to play a game. You know all the rules, inside and out, but you've never met your opponent. There's no history, no data, no tells to read. Nothing. So, what's your play? Now, most of us have probably heard about the Nash equilibrium, right? That's a strategy that's all about experience. It relies on knowing how your opponent tends to play. But what if you don't have that experience? Well, the approach we're talking about today is completely different. We're throwing past performance out the window and relying on pure, cold analysis of the game itself. And this brings us to our core idea for today, max minimization. I know, it sounds a little complicated, but the concept is actually pretty simple. For every single move you could possibly make, you imagine the absolute worst thing your opponent could do in response. You figure out the worst case scenario for all of your options. And then you just choose the option that has the best of those worst case scenarios. You're maximizing your minimum payoff. Yeah, you can think of it as the ultimate defensive strategy. It's basically a playbook for a rational pessimist. Someone who just assumes their opponent is always going to make the most damaging move possible. You're not playing to win big, you're playing to not lose badly. Okay, let's make this real. Look at this game. You're player one. You can choose either top or bottom. Your opponent gets to choose left or right. Your score is always the first number you see in the box. So, for example, if you play top and they play left, you get 2 points. Simple enough? So, let's use our pessimist's playbook. If I choose top, what's the worst thing that can happen to me? Well, a smart opponent is going to see that if they choose right, they can knock my score down to -1. So the minimum I can guarantee myself if I choose top is -1. Okay, so what if I choose bottom? Again, we have to assume our opponent is a genius who wants to crush us. They'll look at their options and see that playing left will, once again, stick me with a score of -1. So the worst case scenario for bottom is also -1. So we have a problem, don't we? The worst I can do with top is -1, and the worst I can do with bottom is also -1. It kind of looks like a tie. Are we just stuck? Do we just have to accept a guaranteed loss? Or is there a smarter way to play this? And this is where it gets really cool. Instead of predictably choosing one or the other, what if you just mixed it up? What if you made yourself totally unpredictable? It turns out that by adding some randomness, in this particular game, it means playing top 40% of the time and bottom 60% of the time, you completely change the math for your opponent. They can't trap you in that worst-case scenario anymore. And look at this. This mixed strategy boosts your guaranteed payoff from a -1 all the way up to a positive 0.2. You've literally raised your safety net just by being unpredictable. Now, this whole idea of assuming the worst about your opponent, it seems, well, pretty pessimistic. But what's fascinating is that there's a specific type of game where this pessimism isn't just a safe bet, it's actually the mathematically perfect way to play. And that happens in what we call a strictly competitive or zero-sum game. In these games, your interests are the complete opposite of your opponent's. Every single point you gain, they lose. My win is your loss, and your win is my loss. There is absolutely no room for cooperation here. And here it is. This is the really beautiful connection. In these very specific zero-sum games, that defensive, pessimistic max minimizer strategy, well, it's not just a good idea, it is the Nash equilibrium. The logical, safe play and the perfect, optimal, stable play are the exact same thing. It's this amazing moment where being cautious is the same as being brilliant. So the theory is just, it's elegant, it's clean, it gives us this really clear prediction for how a perfectly rational person should play. But, that leads to the big question. Is that how we, as actual human beings, really play? So this idea, max minimization, it's actually been around for centuries. It was first described way back in 1713 for a card game, but it wasn't until 1987 that a researcher named Barry O'Neill finally decided to put the theory to a proper test with real people. O'Neill came up with this special card game, a strictly competitive one, of course, where the theory made a very, very sharp prediction. It said that, to play perfectly, players should choose to play the Joker card exactly 40% of the time. Not 39, not 41, exactly 40. So what happened? Well, the results were just fascinating.
On average, people play the Joker about 36% of the time. Now, at first glance, you might look at that and think, hey, 36 is pretty close to 40. That's a win for the theory. But as anyone in statistics will tell you, close isn't always close enough. And here's the twist. When the proper statistical tests were run, that little 4% gap was actually a huge deal. The theory, the idea that people naturally play this perfect rational strategy, was decisively rejected. It turns out we are not the perfect logical machines the theory predicts. Okay, so this might feel like a bit of a failure, right? This beautiful, elegant theory didn't quite hold up when faced with messy, real-world humans. But that does not mean the model is useless. Not at all. Far from it. So, does this experiment mean we should just toss the whole idea of maximization in the trash? Absolutely not. Its value just isn't where we might have expected it to be at first. You see, this theory gives us 4 incredibly useful things. First, it gives us a powerful baseline, a crystal clear picture of what pure, logical rationality even looks like. Second, it's a practical tool you can actually use to guarantee yourself a minimum level of safety in risky situations. Third, it acts like a ruler, letting us measure exactly how and by how much our human behavior strays from that perfect logic. And finally, it's a bit of a reality check. Because even though this theory isn't perfect, the evidence shows that so far, no other single theory has been found that's systematically better at explaining how we play. So in the end, we're left with this fundamental choice whenever we face a strategic decision. In a high-stakes game, do you trust the math, that pessimistic logic that guarantees you a safe floor and protects you from disaster? Or do you trust your gut, playing the person across from you, not the odds, hoping to exploit a human flaw for a bigger win, but also risking a much greater loss? That right there is the real game.